Hello there. In this video we're going to continue our discussion of the exponential continuous random variable. So recall that the probability density function for an exponential RB is represented by the density function f of x is equal to lambda e to the minus lambda x for all values x that are non-negative, and it's defined to be equal to 0 if x is negative. So we're going to be deriving the moment generating function for this random variable and also discussing and deriving a couple moment properties for this random variable as well. So, as usual, we're going to begin by using the definition of the moment generating function. So recall the moment generating function for random variable x of parameter t is defined to be equal to the expectation of the random variable e to the t x, where x is a random variable. So I'm going to find the expectation of this distribution. So by definition, that's of course going to be equal to the integral from minus infinity to infinity of e to the tx times our density function f of x. So as we already know, this function is 0 on the left-hand side of the real line. So we can rewrite this integral from 0 to infinity since the left-hand side is going to be equal to 0. So this integral then turns into the integral from 0 to infinity of e to the tx times our density function lambda e to the minus lambda x dx. So both, well, first off, this constant lambda can come outside. So this is just precisely equal to lambda times the integral from 0 to infinity of e to the tx times e to the minus lambda x dx. We can then combine our exponents. So since they have the same exact base, it's the same as e to the tx minus lambda x, and both have an x term in it, so we can rewrite that as e to the, let's see, that's going to be t minus lambda x. So this is going to be lambda times the integral from 0 to infinity of e to the power t minus lambda x dx. So t minus lambda is a constant, so this is a very easy integral to evaluate. So it's going to be lambda times 1 over t minus lambda times e to the t minus lambda x, evaluated as x goes to positive infinity minus the valuation as x goes to 0. So as x goes to infinity, this is going to go to 0 if this term is going to be negative. So it's only going to be negative if lambda is greater than t. So if lambda is greater than t, then e to the t minus lambda x is going to go to 0. And when we plug in 0, that's going to go to 1. So this is going to be equal to lambda over t minus lambda times. So infinity, we're going to assume this case, so that's going to go to 0. Minus, that's going to go to 1. So 0 minus 1 is negative 1. So this is going to be equal to negative lambda over t minus lambda, or equivalently, lambda over lambda minus t. So this is the moment generating function for an exponential random variable, and this is true if lambda is greater than t. Now, is this scenario satisfactory? Well, typically the average of an exponential random variable is usually a positive number, and to find the moments of random variable using the MGF, usually this value t is evaluated at 0. So since lambda is typically a positive number, t is going to be plugged into 0, then this restriction is actually satisfactory. All right, so let's find the expectation of a exponential random variable. So using the moment generating function, we know this is going to be equal to the derivative of the moment generating function mx of t evaluated at t is equal to 0. So that's of course going to be equal to the derivative with respect to t of lambda over lambda minus t evaluated at t is equal to 0. The bottom is the only variable expression, so we can rewrite this as lambda times the derivative with respect to t of lambda minus t to the negative first and we're going to evaluate this derivative at 0. So using the chain rule, this is going to be lambda times -1 times lambda minus t to the minus 2 times minus 1, all evaluated at t is equal to 0. So the two negatives make a positive, so this is going to be lambda times lambda minus t to the minus 2, evaluated at t is equal to 0. So when t is equal to 0, that's just going to be lambda over lambda squared, which is going to be 1 over lambda. So this is the expectation of an exponential random variable. So we're going to move on to the second moment of an exponential random variable, ex squared. So by definition, that's going to be the second derivative with respect to t of the moment generating function mx of t, again evaluated at t is equal to 0. So what I'm going to do is I'm going to start with the first derivative, and then I'm going to take the derivative of it. So this is going to be equal to the derivative with respect to t of lambda minus t to the minus 2, evaluated at t is equal to 0. So again, by the chain rule, that's going to be equal to lambda times minus 2 times lambda minus t to the minus 3 times minus 1. Then we're going to evaluate this at t is equal to 0. And you may start to see that there is going to be a pattern. For example, this -3 is going to come down again if we differentiate for the third moment. And these two negatives are always going to create a positive number. So we can actually just rewrite this as, let's see how I want to write it. So this is the same as lambda times 2 factorial divided by lambda minus t to the positive 3, evaluated at t is equal to 0. So when t is equal to 0, what is that? So that's going to be 2 factorial times lambda all over lambda cubed. So that's just going to be 2 lambda over lambda cubed, which is the same as 2 over lambda squared. So that's the second moment of an exponential random variable. In general, you can find that the nth moment of an exponential random variable is actually going to be equal to, so once we bring down the 3, that's going to be 3 times 2, so that's going to be 3 factorial. So you're eventually going to see that it's going to be n factorial all over lambda to the n. But at least for basic statistics, the first moment and the second moment are usually the only ones that we care about. So ex and ex squared. So from these two, we can generate the variance of an exponential random variable. So the variance, as we know, is going to be equal to the second moment minus the square of the first moment. So the second moment, 2 over lambda squared, minus first moment squared. So we have 2 over lambda squared minus 1 over lambda squared. So it's going to be 1 over lambda squared. So it's going to be the variance of an exponential random variable. So from here, we can state that the standard deviation, or just sigma x, is just going to be 1 over lambda, which of course we know is equal to the expectation of an exponential random variable. So that's a useful, so if x is exponential. And this does share a relationship with a discrete random variable, so recall the Poisson. The Poisson has the property that the variance and the mean are both equal to lambda. So these two distributions are actually related intimately, but we're not going to get into that discussion here. But for here, we've derived the moment generating function for an exponential random variable, derived its general formula for the nth moment, and also proved the standard deviation first moment, second moment, and variance formula for an exponential random variable.